restoration?
What do you mean by dynamic response?
Do whatever you want to do. Because the battery's not going to be coupled to the grid. It has to go through a power converter. The power converter is what determines the dynamic response.
But what do you mean by dynamic response?
Like how quickly can they? We know that nuclear cannot respond.
Oh, the dynamic response from experience, not from published literature, from experience is a couple of minutes. Published literature will tell you it's about 30 seconds, sometimes cycles. But
Really?
yeah.
For batteries?
Mm-hmm.
That's awfully slow for my rate.
For black start, it's about 2 minutes.
Oh, for black start.
Yes. Yes.
That's what resiliency is, right?
It's mainly for us. It's mainly we're talking about black start. When you have an outage and you come back and try to start islanding, in that sense. Now, if you're grid connected and you're just transitioning without any outage scenario, you're just transitioning between grid connected to islanded and vice versa, and both are live. And the reason you're transitioning from one to the other is just economics. You want to run your island because it's more economically to run it your own. That's a different story. Yeah, but black start from experience, not from studies or published literature that assumes a lot of assumptions, is about a couple minutes, 2 to 3 minutes. Yeah, yeah. Okay. So let me see if I can click on the slides. That didn't work. Click here. Nope. And click here. Maybe that. Or that. Okay. All right. You're all familiar with Ameren, Illinois. I hope. I've talked plenty about it. But if you need me to remind you, I can. So during the overview, I was talking to the IEEE chapter about my team and what my team is responsible for. So you probably have heard me talk about all this stuff, but my team is responsible for policies and standards for integration of DER and interconnections to the grid. We do hosting capacity work. We do DER valuation, which we'll talk about today. We have a team. We have members that are looking at DERMS design and implementation. DERMS is distributed energy resource management systems, and we have folks that are looking at non-wires alternatives as well. What was really interesting, the folks that I went to SIUE to present about DER value, and the engineers there, if you ask them about what's a DER, a lot of them didn't really know what a DER is, and they're all electrical engineering students, undergrad and grad students. So I pulled up a bunch of definitions online for what a DER is, and the industry itself does not even converge on a common definition for what a DER is. So if you take a look at their NERC, National Electric Reliability Council, defines a distributed energy resource as any resource on the distribution system that produces electricity, and is not otherwise included in the formal NERC definition of bulk electric systems. Battery storage, for example, is not an energy-producing asset, right? Battery is just a device that charges and discharges. It does not actually create electricity. So in the definition of NERC, a battery would not be a DER. If you look at NREL's, National Renewable Energy Lab, their definition is it's small modular energy generation and storage technology that provide electric capacity or energy where you need it. EPRI had a kind of a very broad definition. It tells you it's technology advancements in connected loads and PV and energy storage. So what about wind, for example? What about natural gas generation? So you see that the different definitions probably take you different paths when we're looking at DER. NARUC is the National Association of Utility Regulators Council. So they're the regulating bodies all across the nation. They have a really broad definition of DER. I like because it includes a lot of the stuff that we consider to be DER. What I did not see in other definitions, again, happen to be included here. In particular, EVs. EVs are DERs, and a lot of people miss that fact that EVs should be considered a distributed energy resource. By what argument are they a DER?
Yeah.
The fact that they have energy storage on board, and they can have grid to vehicle tap interactions. So the vehicle itself or the battery on the vehicle can discharge onto the grid and can charge from the grid. So it's just like any energy storage device, but now it's on wheels.
There are actually papers of using an electric vehicle to supply rather than consuming. There are papers.
We use it at the Technology Application Center to do that. So when I talk about microgrids next lecture, remind me to point that out. But it's part of our collective assets on the microgrid. We use it as a load. So if you have too much generation, you want to, for example, dampen frequency, you can use it as a load. And if you need some type of capacity support, you can dispatch that asset. Does that make sense, Jeff? Our definition, Ameren, Illinois' definition of what a DER is, we took also a broad definition. And this was in a response of some workshops that we've had with the Illinois Commerce Commission discussing DER in general. So ours is, again, any generation, storage, or load management source that's connected to the distribution system is considered DER. So demand-side management in our world is considered a DER, right? If I can manage demand and loads behind the meter at customer premises or in general, that's part of a DER asset to me that I can use as I operate the grid. Does this make sense in terms of what different definitions have for DER? Okay. Why is DER important? At least for us in Illinois. And I wanted to talk some numbers. I figured, these would stick with folks when they see some of these graphs. So if you look from 2015 to year-to-date 2019, 2015 total net metering installations. Are you familiar with net metering? Kind of, sort of. So net metering is the concept. It's the rate design specifically for distributed energy resources. So for folks that, for example, have solar on the roof, the way their bills are managed, their rates are managed, are under the net metering concept or structure. So if you pass energy on back to the grid or backfeed energy back to the grid, you're being compensated under the net metering framework, right? So that's kind of what governs a lot of DERs that we have on the system. Anything that interconnects on the system is mostly governed, from a distribution perspective, is mostly governed by the net metering concept. So the net metering installations in Illinois in 2015 were about 400. In 2016, about 530. In 2017, they're about 700. And look at that jump from 2017 to 2018. Went from about 700 to 1,400, about 1,500. Almost doubled in 2018 in 1 year, right? And you can see the uptick in residential was really large. And then you see it continues that trend in 2019. We're only 3 months into 2019, and then uptick continues to grow. And we envision this to probably reach the 2,000 by end of year.
Are there any kind of incentives that Ameren specifically provides to the residential user? I know the state has some kind of incentives to install solar at your house. Are there any incentives that Ameren or the utility also gives to
Yeah. So that's a great question in terms of why that jump. So exactly that. The reason for this jump mainly is incentives that the state had that kicked in late in 2017 for folks to start taking advantage of. So the laws, the FEJA law, the Future Energy Jobs Act, that had inside it a lot of incentives for folks to start using distributed energy for multiple reasons, environmental being one of them. Others is that the state has a goal by 2026 to have 25% of all energy produced or used in the state to come from renewable resources. Of that goal, of the 25%, we're only at 7% today. So that's one of the attempts for the state to probably push a little bit more for DER growth and renewable to meet that goal. But in terms of incentives, the incentives that got kicked in the FEJA law are primarily tax incentives. So you get 30% back on your installed cost. The second one is, of course, you continue under the net metering framework. So as you push back on the grid in terms of energy feedback, you get that credit on your bill. But most importantly, back to what you were asking, is there incentives that come from the utility? They come from the utility, but they are paid for by the rest of the customers all across the state. So all the customers in the state will support incentivizing this DER. And the form of what the utility can give in rebate is the smart inverter rebate. that we've discussed in other lectures before. The smart inverter rebate pays $250 per kW just to install a smart inverter. So now somebody that has 30% of installed costs back to them just from state, and then you get net metering dollars, and also you can add on top of that dollars that come from installing smart inverters. All of it make it very attractive financially to install a DER.
So when you say from rest of the customers, like, do you guys socialize the cost among the customers? I didn't understand that. Like,
Yeah, the cost gets socialized. So when I give, for example, if Professor Sauer wants to go install some solar, and he wants $250 from Ameren, we'll give him the $250, and we will put that in our rate base, meaning we'll get that money back. So we gave him the rebate, we'll get it back. But who pays for it? It's everybody else in the state that pays for that. Yeah, that's policy. That's just the nature of the beast. Yeah. Does this make sense? Just shows you that growth, that all that's happening is more and more DERs coming on our grid. I want to show another number, and I figured this may speak more to us as engineers. That's the kW capacity installed of net metering. And again, look at the trend. We went from 5 megawatts in 2017 installed capacity to year to date close to 24 megawatts of installed capacity. This is all DER, right? Most of this is PV as well. Most of it is photovoltaic. So pretty interesting in terms of just looking at the kW. In 2019, the community solars have not kicked in yet. So remember, there's also community solar part of this. This does not include the community solars here because they are not in service yet. But we anticipate another 50 megawatts of just community solar to come online by end of 2019, early 2020. So imagine, again, the growth in DER capacity that's going to continue to be on the grid.
does geothermal count under DER? Like, I know not every place is capable of producing geothermal, but if it's in a place where you can extract some geothermal energy, does that count into DER?
If it does produce energy, then yes. That will be considered a renewable form of DER that counts under this framework. Yes. Do you know anybody that has geothermal?
I know because I was working on a project similar to that, and we were using geothermal for that specific site for HVAC, for heating and ventilation, not to produce energy, but that did reduce energy consumption of the house by a lot.
Sure.
And we had to install less solar because we were spending less energy on generating heat.
Sure.
So that's one of the alternatives. I don't know personally if anyone is using geothermal to produce electricity. But for heating and HVAC, like the house design.
Sure.
Yeah.
So I live in.
It's definitely a thing in Iceland in particular. Iceland is basically a country on top of a volcano. They have extensive geothermal plants.
Sure. I don't know how much truth is in what I'm going to say next, but in terms of the concept. But 2 years ago, I was walking in the park across from your house in Urbana. I live in Urbana. And then I was on a bike with a friend, and then this gentleman was on the ground. He seemed injured. We helped him up. Older gentleman, and his name was Guy. And we asked him, everything okay? He's like, yeah. And he had a wheelbarrow, and he had some bricks in it. And we asked him, what he was doing. He was building a geothermal well, is what he called it, in his house. And he did say that Urbana-Champaign is positioned on top of a great reservoir of water with access to geothermal that's easy and convenient, I guess. So I never investigated the truth, or if that's
actually true.
Is it?
In ENG 572, that's a seminar series that I attended. Professor John Abelson, he's in material science. He actually has a geothermal. He extracts geothermal on his backyard for HVAC purposes. We had a whole presentation on that specific thing for a whole class.
Sure.
It is true.
Okay. Cool.
Is that number cumulative?
Yes, that's cumulative.
That's the current total.
That's current total year to date. Cumulative. Yep. And I don't know. Again, in putting this in perspective, it's probably not a whole lot in terms of the load that Ameren, Illinois customers consume.
Or if you look at what was added in 2019, it's just that.
No, that's cumulative. Yeah, that's cumulative.
Yeah, I know.
Right. Yes. Yep. And what I was wondering, and I asked some folks to look at the numbers, is how does this compare to our load? Because at certain thresholds, 3% of load, to installed capacity, 5% of load to installed capacity, these ratios, we have to act, and do certain things according to the law. And today we are at 0.6% is the ratio of load to installed capacity of DER. At 3%, for example, we have to start this DER value framework. That's why we're talking about this today, at 3% penetration. At 5%, the law says no more net metering. You're going to go away from net metering and you're going to transition to this framework of valuing DER. So based on your value to the grid, from a DER perspective, you get compensated. If there's no value for you to the grid, you don't get compensated. So the net metering concept is going to go away at 5% penetration. That's why also it's important to look at the installed capacity and compare that to the overall load. This just talks a little bit more about the number of applications we got in specific for community solar. So I'm not talking about applications for other residential needs. This is for the community solar. And the community solar is capped at 2 megawatts. So these are 2 megawatt farms, solar farms, that come and interconnect to anywhere on the distribution system. So we have received, year to date, March 2019, 781 applications for folks that want to put community solar on our grid. Look how that trend also grew. Went from 61 about a year ago, 61 applications, to 781. These are 781 applications that we have to study. We have to analyze their impact onto the grid, right? What are they going to cause in terms of issues? What do we need to do in terms of upgrades to accommodate these solar connections into our system? And then most of those won't even go into the construction phase, because they're all competing for dollars that are available. The state, through the Illinois Power Agency, creates a pot of dollars for renewable energy credits. And these folks all compete to get these dollars. If they get them, then their project makes financial sense and they move forward. If they don't get them, they won't, and they will go away. But it puts in perspective how many applications we have studied so far that come our way, and all the analysis that we had to do to figure out what these customers are going to impact and how they're going to impact the grid, and provide good faith cost estimates back to them in terms of what they have to do to be able to connect. Do they have to pay for an upgraded recloser or regulator? Do they have to pay for integrating into a DA scheme that exists? And we'll talk a little bit about that reliability issue and how we determine some of that stuff. Okay, so DERs are transforming the grid. I don't need to say a lot about this, but it was very interesting to see how folks yesterday at SIUE kind of, again, like I said, was as eye-opening to them, the fact that we're going and transition from a radial system, right, a big power plant generation, all the way to the customer, to now you have a network. Everybody can generate at home if they wanted to, and then we have two-way power flow. We have sub-transmission lines that were never designed to have a back feed on it, that now all of a sudden have back feed on it. And what does that cause to the overall system? What are impacts to reliability and to planning and to modeling? These are things that we consider when we're looking at the DER value, right? So when you want to value the DER and figure out what its value is or impact is to the grid, these are some of the things that we consider: the reliability, the planning, and the modeling impacts. Here's a true simulation. So the software you use, showed you last couple times, was Synergy. So this is a true simulation of 3 proposed community solar projects on one of our distribution systems. This is a 12 kV circuit, supports about 1,700 customers, and we have 3 2 megawatt community solar projects that are proposed. One proposed right here, one proposed right here, and one proposed right here. The beauty of this circuit is, originally this circuit would have operated without voltage optimization. Remember, we talked about voltage optimization last time, right? And voltage optimization aims at what? At reducing the voltage at the feeder head, at the circuit, and all along the circuit to maintain a low voltage profile on it. So without voltage optimization, this circuit probably would have seen a lot worse conditions. But let's talk about voltage optimization. So the expectation is that the feeder head, we are showing something that close to 122 volts to maintain about 122 to 120 volt profile all across the circuit. With the addition of these three solars, look at the voltage values or magnitude all across the circuit. We're showing about 126 here. We're showing it also close to 126 on 2 phases, on 3 phase one, on C phase 125. At the feeder head, we're at 124. And then here at the end of this circuit, we're showing 127 in terms of volts. So we're already in violations here. This is simulation, right? We get the application, we plug it in, we run power flow on the circuit. So here we're already in violation. That's violating our voltage limits by raising the voltage all on that side of the circuit. So this is some of the basic impacts that DERs could have on our system. So what would you propose as a solution to try to overcome this violation? What would you propose back? As engineers that are familiar with the distribution system a little bit, we've talked a lot about distribution for 6 lectures now. So give it some thought. What would you tell my engineer to do to come up with a solution for that over voltage condition that we've got on that section?
Are you guys implementing voltage optimization on that feeder yet?
We do, and I want to point out that you have a cap bank here that's switched, that's closed, and then you have a fixed cap bank here that's also closed. Maybe that gives you a hint. There you go. So that would be one of the first things that we would do is come here and say, okay, we know that voltage is tied very, or correlated really, really strongly with VARs, right? I assume that because that cap bank is normally closed under normal conditions, right? It's closed there. Typically, we run our cap banks on time and temperature parameters. So at a certain time of the day or a certain temperature point, I want you to come on, right? So it comes on, say at 9 a.m. in the morning, or if the temperature reaches 72 degrees, for example. These are just some of the parameters, global parameters that we put in our cap banks. So that could have been the reason why this switched cap bank was on, right? If I open that switched cap bank, I'm basically eliminating some VAR flow here that could help bring that voltage down. How much is it going to bring it down? I don't know, but that would be one step towards trying to solve the problem. What else may I suggest to the customer or to my engineer to try to help resolve the issue?
Dimmer switches.
Dimmer switches for the loads, so their lights won't burn out. One could suggest trying to figure out what that impedance on the line here, and maybe reconductor to try to help with that voltage drop that you've got on the circuit. That's one thing you could do. Voltage regulators typically don't help. You could think of voltage regulators here, but voltage regulators don't respond real quick to voltage change, especially if you got cloud coverage that comes over the solar farm that could keep spiking up and down the voltage. So they can't react fast enough. They need a few minutes before they can react. They see the voltage, the logic kicks in, they start tapping up or down. So voltage regulators can't react fast enough to cloud coverage that's moving in milliseconds, maybe seconds. So reconductoring is one thing that we typically look at. One thing that we've right off the bat asked the customer, can you reduce your overall production on the circuit, right? Go instead of 2 megawatts or 2 MVA, can you do 1.85? Because we will run a simulation, we'll see what 1.85 will do, and if that will solve your problem, we'll go back to the customer and say, hey, can you put some control logic on top of your inverter, right, or in your inverter to reduce and limit the amount of kW that you want to produce? And why is that? Is that because that could be a cost-effective solution for the customer. Instead of us going and adding controls to the cap bank or reconductoring or doing other things to the circuit to try to eliminate that problem, right, we can go and say, hey, if you limit to a certain amount of kW that comes out of your farm, that could solve the overall problem. Nobody has to pay any money moving forward. Does that make sense?
What's the concept of reconductoring?
It's just using a different size of conductor that could help you reduce or increase the impedance on the line to solve the voltage problem. So you're just controlling the impedance in here to try to control the voltage drop on the circuit.
And how do you implement that in real life? Like, how do you change the conductor?
You replace it. You go up on the pole. You cut down the old conductor. You string a new conductor. Very costly.
Yeah.
Yep. That's why you don't want to suggest it to the customer unless that's your your only and last resort. Yeah. Does this bring to light some of the reliability issues that we could see when customers want to come in and start connecting DER? And this is large DER, right? This could be a distributed fashion where all these customers here start putting solar panels on the roof. And the distributed fashion of that could have a larger impact. I don't know, again, depending on the studies, but we've seen some circuits that have a much bigger impact when you have distributed DER, meaning all these customers start putting solar on the roofs rather than having a centralized community solar that's connected at one single point on the circuit. So different scenarios provide different challenges for us, and our engineers try to figure out the best way to remediate some of these issues. Here's another example, and we've talked a little bit about this, but I wanted to bring actual scenarios to you, live scenarios to you, so you see what I'm saying is not smoke. This is a distribution automation scheme between two circuits. Remember our distribution automation discussions, right? Distribution automation, we're using automated reclosers that have sensing on both sides, that have communication built in them. So if you forget anything we've talked about DER, I want to make sure you know what we do from a distribution automation perspective, which is, again, how we use these intelligent switches to reconfigure our circuits. So if I have an outage on this section here, where team 1 exists, right? The idea is I should be able to restore team 2 from the adjacent substation. This is a normal open point between the two circuits. If I lose this section, the idea is 325-1 will open, 325-0 will open, isolating that problem. And then we will check to see if substation B can pick up the load on this section. And if it can, that normal open will close automatically. All this happens, of course, in seconds, but that's the logic behind it. Does this make sense? Just want to make sure we're on the same page. Okay, so how does DER impact that? So let's go through a real scenario where you would have a fault and what the 2 megawatt solar is doing in that case. So if you look here, substation A, its pre-fault load amps were 50. So I am serving 50 amps on recloser 325-0. Substation B, its pre-fault load amps is 100. And its capacity, meaning the total amount of amps it can handle, the substation this side, is 200, right? So I can handle an additional 100 amps. So if I'm feeding 100, I can handle additional 100. So far, so good? Okay. If I lose substation A, if I lose this source here, right? Just like we talked about, 325-1 and 325-0, this one and this one will open, sectionalizing this side. The ITR in the middle, the normal open one, can close and pick up the 25 amps that we've got on this section. So far, so good, right? Because I had a additional capacity of 100, I can pick up 25 easily. So how much capacity I have remaining here after I pick up this section? 75. Yep. So 100 is how much I can handle. I just picked up 25. So I have 75 amps that I can handle still from A if I wanted to pick up here. Make sense so far? Okay. So 325-1, this guy now wants to close, right? So we can pick up this section. I've lost the source, so I just want to now pick up this section here. So it wants to close to pick up 50 amps, right? The source here can handle 75 amps, so we're good to go. It will close. In reality, that is not the case. This DER here that was producing energy was masking the true load that was here. The true load that I've got on this section is not 50 amps. It's 50 amps plus whatever the DER was producing and picking up. Does that make sense? So this section here is not truly 50 amps. It's 50 amps plus whatever the DER was producing and picking up in terms of amps. In reality, when I have the outage, this will drop offline. There's no voltage source for the solar farm anymore. It will come offline. 1547 will force it to come offline anyway, right? And I have 125 amps on this section in reality, not 50 amps. So that was masking an additional 75 amps. Make sense? This is one of the core problems that we're seeing, where when somebody installs a DER, it's going to screw up our investment in this distribution automation, and I could end up restoring sections of line that I can't handle potentially burning down some conductor in that case, or screwing up and really ruining some of my equipment on the line. This was another example here where I am backfeeding through substation A. So I use the same example, right? The pre-fault conditions are pretty much the same. Just change some of the numbers here. And now this recloser is seeing a 75 amp flow across it. It does not recognize that that 75 amp flow is backflow. That's because my DER is producing enough energy to cover for this, plus it's backfeeding onto the subtransmission. So when I have a fault condition on A, this source now is going to think I have 75 amps plus 10 amps, so 85 total amps that I need to pick up. Where this can only handle, in this case, it can only handle 75 amps. So just a different source, different data point. It could handle 75 amps, but it thinks it needs to handle 85 amps, when in reality it does not need to handle 85 amps. I don't have enough load here. I'm actually backfeeding. So I should be able to handle this entire load easily. So I just wanted to bring some real scenarios, real data of what we've got here that are impacting our DA schemes.
Can you fix some of it by using angles?
You could if you got a way to
adding amps,
yeah, that's it.
like an electrician.
Right. The easiest way to solve this that we found and we're implementing right now is simply adding a basic device here that would communicate what the DER is actually producing and how much amps it's actually picking up. So now you can just add that as basic math to the rest of your calculations. Yeah, so there's no masking. So we come here and we install a basic device. It's actually a switch. It's a vacuum bottle switch, and it's got metering on it. And you come here and you basically feed that information to the rest of the teams, and it becomes part of the overall team. And now there is no masking that's going on anymore. But like Professor Sauer said, you can do some math. You got all the data, and you can do your own math. You can calculate angles if you wanted to. You can do that in a centralized location. And different vendors are providing different solutions. So this scheme here, we use, for example, SNCs and interrupters. SNC would give you a device that goes here that would connect to all their interrupters. G&W will give you a different device that could go in here and communicate to their logic. Some would use just SCADA. So central blocks that sees all this stuff, runs a basic calculation, right? Runs some estimation, can be able, to tell you how much amperage you could and you could not pick up. So there are ways to solve it, but these are, again, some of the basic reliability problems that DERs are presenting to our systems. Any questions on that so far?
You mentioned for a brief that 1575 or 1545.
1547.
Yeah, what is that?
1547 is an IEEE standard that governs the operations of smart inverters. And in particular, it used to be an anti-islanding rule or standard. The idea there is when you have an outage, you don't want all these DERs to be still connected to the system and trying to provide energy to the system. That creates an unsafe situation for workers on the grid. That's one. So anytime you see a disturbance on the system, the idea is to give ample time for the DER to drop offline. So it monitors frequency very closely, deviations in frequency very closely, and it monitors deviations in voltage very closely. And as those occur on the grid, the DER will drop off within a certain amount of time, seconds, offline, anytime it sees a disturbance, so it does not contribute more to the problem or add additional problems to what's going on the grid. That's 1547. You can just research it. There's plenty of summaries on it, but it's an IEEE standard today. Anybody that wants to connect to the system must be compliant with 1547. So remember when we were talking about why is it important to look at the ratio of load to net generation? That's because portions of the law, like I said, require us to do things as utilities when you reach certain thresholds. So here's an excerpt from the law, right? Just basic copy paste. And what it says here is that to determine the value of DER rebates, once the total generation capacity of net metering reaches 3%, the value of the rebates shall reflect the value of the distributed generation to the distribution system at the location, right? So it's geographic at the location at which it's interconnected, taking into account geographic and time-based benefits, right? So it's time and geographic-based benefits to the distribution grid, right? We're not talking about any additional benefits to the rest of the power grid, not to the generation, not to the transmission. It's the value of the distributed generation to the distribution system. It's a very important distinction as you read the law. What folks that read this piece of law also are arguing that, is it DER or is it DG, right? So here it says that determine the value of DER rebates, right? But further on in the law it says reflect the value of distributed generation. And the reason I started with all these different definitions for DER is because they're different. Is it DER or is it DG? What does the commission want us to do? Look at DER or DG. So again, when you open this up to the public and you got all kinds of stakeholders, everybody has an opinion on what you should be considering and whatnot. The most important piece that we all agree on, it's the value to the distribution system, not to the generation side of the grid and not to the transmission side of the grid, but specifically to the distribution system. So when we look at the value blocks overall of DER, right, and this is across the spectrum that we've got, there are different things that we can consider. There are plenty of papers that are trying to address this concept. What is the value that DER could provide to the overall grid? One can consider, for example, from a generation perspective, the avoided energy generation cost and line loss reduction, right? If I'm producing energy on the grid, I'm avoiding a unit of energy being produced up at the power plant level. Does that make sense? So avoiding that cost has some value to somebody, right? What is that value? But this is the basic concept that somebody can start looking into. So the avoided cost of generation is one value block that somebody could consider. Line loss reduction. When you have a DER that's providing energy on the system, you reduce losses. When you reduce losses, again, that gives you a little bit more capacity upstream, and in particular from a generation perspective. So these two add together under that generation umbrella, and there is value to the generation system by having DER on the grid. Back to the capacity concept. So from a transmission perspective, a lot of the bills that we pay, a big component of them is the capacity cost on the transmission side. So I forget which class Professor Gross teaches, talks about LMPs. Yeah. Electricity markets, 530. 530. Is it 530? Oh, by Bose? Oh, okay. Okay.
It is now.
Oh, it was by Professor Gross.
I took it with Gross probably, yeah. I remember taking it with Gross. But it's interesting. It talks about LMPs and teaches you that why do LMPs exist or why LMP does not equal to 0 is because you have transmission costs.
598 by Professor Gross. It's going on right now, electricity market.
Well, Bose is also teaching 530.
Yeah.
Right. And if you
But he was told not to teach too much.
OPF. Optimal power flow, yes. Constraint OPF and security constraint OPF, that's all 598 now? Okay. I don't remember the names of the classes, but I remember taking them with George. And it's very important, right? It's a very important concept and just gives you a glimpse of how do we actually account for capacity constraints and why these actually have costs associated with our bills. Why do we pay that number? But when you have DER on the system, that could reduce some capacity constraints that you've got on transmission side. That could lower the transmission cost. So again, it has value from a monetary perspective to both generation and transmission. The environmental people jumped in and they said, oh yeah, there's value from an environmental perspective, right? You're helping us achieve our goals. You're avoiding our compliance costs. So there's a value there. Somebody should consider the environmental value for DER. Ancillary services. You could help, theoretically, depending on where you're connected on the grid, depending on what market is open up to you. So PJM's market allows distribution assets to jump in on the ancillary service market. You can do frequency reg with a device that's connected on the distribution grid. In MISO's world, you can't do that. There's no market open for you to do frequency reg from a distribution perspective. It's coming, but it's not there yet. PJM already has it. So ancillary services, somebody could help frequency regulation all the way from the distribution system and get paid for it, right?
How does that market work? Could you elaborate a little on that?
Sure, high level. It's a pretty broad. In 598, they cover ancillary services, but frequency on the grid is as we all know, is very important. It bounces between 60.2 and 59.8, kind of, sorta. It's in that range. Yeah, somewhere in that boundary. And it's been a while since I actually looked at the actual numbers, but that's where it bounces. And we try to keep it as tight, as close to 60 as possible. Anytime it goes overbound, you got all kinds of problems. Anytime you go below that, you also got all kinds of problems. So we try to keep it as sync as possible at 60, right? So when it's going up, when it's going above 60, so let's say 60.1, you want to bring it down. What do? You need more load connected to the system, right? If it's 59.8 and you want to bring it up, you need more generation to come on the system. So that's what a DER can do. If you need more generation, a DER can come online and provide that generation to you, and you get paid for that service to keep the frequency within bound. A battery could be a perfect example of discharge and charge, because it could be a load and it could be a generation source, right? It could discharge energy and charge energy, so it could truly help from an ancillary service perspective. Not only could help because it charges and discharges, but it helps because its response is extremely fast. You asked about the dynamic response of energy storage, right? Its response is extremely fast to these type of events compared to a power plant. Power plant takes, I don't know, 15, 20, 30 seconds maybe to respond to an AGC signal. A battery could respond under 4 seconds to an AGC signal, right?
It can go faster.
Faster than that, but within that range. So you could get paid for performance in PJM's market. If your performance is really good, meaning you respond to that signal within, again, under 4 seconds, you get paid higher than somebody that responds a lot slower. Plus, whatever value you provide in terms of kW, charge or discharge, you get paid for that.
In the PJM market, the signal that you're talking about, is it called a Reg D signal?
It is. Yep, that's it. Does that help? There are other ancillary services. I talked about the regulation market from a frequency perspective. There's voltage support to it. There's reserves. There's a host of, I think, services under the ancillary services. Is that me? Sorry. And then folks came in and said, also there is value to the economic development within communities, right? So if I got, X amount of people that are going around and maintaining now solar panels or installing solar panels, technicians, for example, these are folks that are growing jobs in the community. So there's value for DER in that sense as well. So again, I just wanted to throw out high-level concepts or building blocks for the valuation that folks are considering all across our industry for what the value of DER could be. But let's go back and focus more on the distribution side. So what value truly do we think DER provides to the distribution system? And these are things you all can think about. As master's students and as people related closely to the distribution field, I would value your opinion as well on what do you think DER can provide to the distribution system. But today, DER, under the definition of the law, is renewable DER, meaning we're only focused on solar and wind. We're not focused on battery or natural gas generation, anything like that. Under the law, we're focused on solar and wind. So we're trying to evaluate how could solar or wind or renewable form of DER provide value to me on the distribution system. One of the basic ones that we could think of was the distribution asset deferral. Think of a transformer that's overloaded. I take a look at a transformer, it's feeding a subdivision, and that transformer is getting to its limits, especially in the summertime, peak time, right? Customers are using a lot of energy. That transformer is humming really hard. It's right at its limits. What typically utilities do is they do 5-year forecasting and try to replace that transformer before it fails. So to replace that transformer, that's cost that the rest of the customers will have, again, to pay for. However, if DER can come in and support during these hours where the transformer is being overloaded and defer the investment, instead of investing in it in 5 years or in 2 years to replace it, I can now invest in 7 years or in 10 years to replace it, right? There's value in that because now I'm pushing the cost out in the future. I'm not paying as much for it. So there's value in that. That's what we call the distribution asset deferral. You can apply the same concept. Instead of a substation transformer, it could be a conductor. A conductor out on a line that also gets close to its limits that we project in 5 years as load grows, is that conductor is going to be overloaded. And I need to do a reconductoring project, just like we talked about. Strip out the old conductor, bring in a conductor with more ampacity and thermal limits. To do that, that's a big job. That's a lot of cost. However, if there's DER that starts growing around that area that can support during these hours, and the key here is support during the hours, right? If it supports me during low peak hours where there's no need for additional capacity, there's no value there. That's where time and performance is key. So geographically already identified. It's got to be around that conductor, around that distribution transformer that's being overloaded. Time is what hour of the day is it? Is that the time that I need the help on that conductor or on that transformer or not?
How do you correlate the intermittency of renewable with this value? Because let's say there's a peak hour requirement and there may not be enough solar or wind generation. So how do you correlate the value to the, like it's not always available, right? At peak hours, renewable won't always be available.
Right, right.
So then it's not providing any value.
Right. So there are two things that you could think about. Not necessarily that I'm doing, but you could think about. One is overlay on top of your hourly performance of your asset what the solar or wind profile is going to be. Right. So if my solar profile looks something like this, right, this is your time of the day, and my solar profile comes up, for example, something like this, and say comes on at 8 a.m. and then goes out at 6 p.m. Right? I overlay that on top of my hourly chart for demand on that transformer. Right? So this will be my transformer demand. These are the loadings on my transformer. And I can see that, for example, here I got no help at all from solar because solar does not even come on. So any of these hours, there's no value for solar. Right? Here, I don't have any problem. It's not a loading problem, although solar is available. So I don't have a problem there. Here, I have a loading issue, for example, and solar is available. It could chop that peak. So you just overlay the two profiles on top of each other, but you have to do a time series analysis. It's going to be hour by hour for the entire year, projecting what the profile of your DER is going to look like and what your demand is going to be. This goes back to what I was talking about, and I think it's in further slides. But the need to look at impacts to planning and modeling, right? How do you model that DER is going to be extremely important to you? How do you forecast that DER is going to be extremely important to you? And then how do you forecast your load? If my load is not going to grow and I incorrectly forecast is going to grow, then all my calculations are going to be messed up. So what sources of information do you use to forecast both the generation and the load is extremely important to try to figure out that lineup of is there value for the DER or not. Does that make sense? So one of the other thoughts is to do also similar to on-off scenario. Remember when we talked about conservation voltage reduction and VDO, we were doing on-off scenario with voltage reduction, without voltage reduction, try to capture that difference in performance. You can do the same thing here. You can have your network model, no DER on it, run it for the next 5 years, and tell me what violations do you have. And then start adding DER on your assets and rerun and iterate through that to try to figure out, okay, where are my violations now being eliminated and where the source is, and try to capture that value in watts and bars. Make sense? So that's from a distribution asset deferral. There is value there, and these would be some of the methods that somebody could think about to try to compare it. Volt-VAR support. So we've talked about that scenario where we had the voltage here in terms of issue. You could think of this as an area on the distribution system that needs voltage support. This could be an area where the voltage is actually extremely low naturally before you add DER to it. And instead of me going in and adding a cap bank to help with that voltage, I say, wait a minute, it cost me 30 grand to go put a cap bank. If a DER can come here, there might be value to the DER that's cheaper than 30 grand, but I can compensate that developer that has DER there that could help me during these hours where I need voltage support. Right? So you could do the same exact thing for the voltage piece, trying to understand its value to the grid where you have that constraint. So again, it becomes an exercise of running your model, right? hourly time series, try to figure out where your constraints are in terms of voltage and reserves or capacity, and then overlay that with DER to try to figure out if DER can provide that type of support back to you or not. Then you start thinking about maybe reliability. So we talked about capacity, we talked about volt and VAR support. Let me also pause here and talk about the other elements. So here we talked about generation and avoided energy cost. That's not a value to the distribution system, right? The avoided generation cost is something that plays in the market on the generation side. There's no value to it from a distribution perspective. I eliminated that. So here you got to focus only on the value to the distribution system, to the poles and wires on the distribution side. Reliability is tricky because it's not technology agnostic. So distribution, asset deferral, and volt VAR support, any DER can provide capacity by virtue because it's providing generation energy, and provide VAR, right? That's by definition. It provides both from an energy perspective. But from a reliability perspective, that's what we talk about in specific for outage scenarios. So if I do have an outage on my circuit, right? Can your solar provide you energy at home and offset that outage that the utility would have had? Can it? Can it not?
It's not a good idea to have that planned.
Well, first of all, it can't, right? I want you to remember that because it needs a voltage reference. If I lose the utility, there is no voltage reference unless you have energy storage or battery. So that's what I'm saying. It's not technology agnostic. You got to have specific technologies that provide that element of reliability to you. So just because I have solar panels on my roof does not mean that when the utility grid goes down, I'm going to have energy. Right? It needs that voltage reference coming from the grid unless you augment your solar panel with a voltage source like a battery, a fuel cell, an engine, right? Or a generator. That's how you get that voltage reference and that's how you get that reliability. Same to your neighbors.
Are you wrapping up?
Yes, I should, right? Yes. Yeah. So let me maybe pause here. I think that we have one more minute and see if there's any questions. I mean, the rest of it just talks about where the data should come from and maybe the overall model. But any questions?
So in your current definition, you said you guys are only considering, not you guys, but state is only considering solar and wind, the renewable as DER.
Mm-hmm.
There's no battery. So in terms of reliability that you were speaking, there's no voltage reference, right?
Right. Right. So yeah, so when I'm investigating that for that type of DER, and I'm trying to run the analysis, there won't be value for reliability for that type of DER. If it's coupled with another type of DER, like battery, there might be, but under this framework, I'm only supposed to study the renewable piece of it. Now, for everyone's purpose, we should study the framework with all DERs. Consider every type of DER and how it could provide value to the grid. Other questions? Let me pause this while, because I think we stopped the recording. So Kevin would be happy.